So, welcome back in our video lectures on projective geometry. Last time we learned about cross ratios seen from a specific point, and this time we want to collect various interesting and useful properties of such cross ratios. So you may remember last time we defined the expression AB with respect to CD seen from a point X for four given points A, B, C, D and one given point X as the quotient of this product of determinants, and we proved that this is indeed a projectively invariant function. Now we want to investigate how invariant this function is under even other operations than just projective transformations and rescaling of the representatives. So one thing we want to investigate first: what happens if we move one of those points into the direction of X. So you remember this is called the cross ratio of the 4 points seen from X, and if you are at position X you don't see any difference whether A is here or A is here. It's just a point on the same line, and you only from your perspective viewpoint only see that line, and as a matter of fact this expression here turns out to be invariant under such an operation. So let us do a little calculation here. So we give coordinates to these green points as a linear combination of A and X, and well, all points that satisfy such a linear combination here are points on the line joining A and X, but we also make sure that this prefactor of A stays away from 0, because if it were 0 then the green point would coincide with X, and this we want to exclude. So we assume the green point is any other point on that line except for X. So what happens if we substitute this term in our expression of the cross ratio? So here you see we replaced A by the linear combination, and well, you all know the determinant, and the brackets here are a determinant, is linear in each of the columns, so we can factor out this expression, and if we do that then we get this longer expression, which at first time seems to be more complicated, but in fact is simpler, because here you have a determinant that turns out to be 0 because X occurs twice in it, and here you have another determinant that also turns out to be 0, resulting in, well, that we just can neglect those two summands here, and we are left with this expression here. And well, if you look at that expression, we claimed that lambda should not be 0, so we can also cancel lambda, and we end up, well, exactly with the same expression we had here. So our cross ratio seen from X does not make any difference if we replace one of the points by a different point on the line that joins it with X. This is not only true for point A, this is true for all the other points as well, and therefore we can say, well, let's replace the other points as well, and call those new points A prime, B prime, C prime, D prime, and we say by the same reasoning that the cross ratio, well, is the same if we replace all red points by the green points. This is a nice and handy formula, and it helps us to use cross ratios as a kind of coordinate system for projective configuration. So coordinate system which has the property that it remains stable under projective transformations. You may remember my analogy from the last video about the little birdhouse, where I had those wooden pieces and measured the wooden pieces and said, well, the fact that we can assemble the birdhouse from those little wooden pieces relies on the invariance of measuring distances and angles along those pieces, so we can safely move one piece to a different place. And the same now happens with our cross ratios here. So assume we have the following situation. We are given 5 points, and so the 4 yellow points should form a projective basis, so no 3 of them should be collinear. So in principle, by projective transformation, we can move them to an arbitrary position. But what happens if we have an additional point P? So if we know a little bit of cross ratio information about that point P, we can uniquely reconstruct its position. So assume we are given this cross ratio here, which is essentially all 4 points seen from point V, and this cross ratio here, which is essentially all points seen from point W. Then the first cross ratio tells us that whenever we already chose positions of the 4 yellow points, then the green point P has to lie on a specific line, this one here, whose position is determined by the value alpha. And similarly, if we know this cross ratio here, we know that if the yellow points are fixed, the green point has to lie on a certain line here, which is given by the parameter beta, and the intersection of these two lines really uniquely defines the position of point P. So we can really think of the cross ratios as a kind of coordinate information that helps us to reconstruct a configuration up to projective equivalence. There's something more you can do with this expression and the possibility to shift your points, and we will investigate that now. What you can do in particular, you can move your green points to a situation such that they become collinear. And well, we just saw the cross ratio didn't change, and even if we move the red points to a collinear situation, the cross ratio doesn't change. And actually, if we take any line like this here and intersect this line with the 4 blue lines, we get 4 points, which will have the same cross ratio as we originally had. So in principle, we can speak of the cross ratio as a kind of invariant property of our 4 lines. Let's call them for a moment A, B, C, D, and say, well, actually the cross ratio is a projective invariant of those 4 given lines, because no matter which line we take for intersection, if it's this one, or this one, we will always get the same cross ratio. I want to go even one step further and show you that the cross ratio is even independent of our point X if the following happens, that our 4 points here are really collinear. And for that I need to recall some information from hopefully your linear algebra class. You should hopefully know that if you want to calculate the area of a triangle, so you are given 3 points A, B, and C, and you want to calculate the area of that triangle, it turns out to be the following size, the following measure. You have to take the determinant of your 3 points in standard embedding. You need a 1 here, and the determinant turns out to be exactly twice the area of the triangle. Here I have one little word here. I say oriented area, meaning that this area really has a kind of orientation. If A, B, and C are ordered in a counterclockwise order, this will turn out to be a positive sign, like here. If they are in clockwise order, the sign of this determinant will be negative. It has to do with the right-hand rule of the sign of 3 vectors in R3. So here in our cross ratio, we have determinants, and we see that determinants of points in standard embedding are essentially areas. Well, do we have to care about the standard embedding? Not really, because the cross ratio was invariant under arbitrary projective transformation and under rescaling of the points. So no matter which points you give me, I can always move them in a way such that all of the points, if it's only finitely many, are in a finite position, having non-zero entry here, and I can rescale them such that they have a 1 here, and I'm in the standard embedding. So moving points into the standard embedding doesn't change the cross ratio. So we can freely argue within the standard embedding. So what does it mean? We can easily substitute those determinants here by our area functions and do the following replacement. So the cross ratio is essentially the same expression, just with the determinants replaced by areas. You may remember those factors of a half that were floating around, but they cancel out because we have things happening in the numerator and the denominator. So we have this area. Let's for a moment think about the area. I think you remember that if you have a triangle, then the area can be calculated as the altitude times the baseline divided by 2. So you get h times g divided by 2 for the area. So we can replace our expression of the area by that. So here I've drawn the triangle AXC, which plays a role here, and replaced it by that formula, and I did the same thing for all the other 4 areas. And now I have to comment for 2 reasons about that formula. First reasons, I use those lengths here, and I have to consider them as oriented lengths, meaning I fix an orientation of this line, and depending on whether A and B run in the direction of this orientation or run against the direction of this orientation, this oriented length is positive or negative. First comment. Second comment, you see that I only used one h here. So I used the same h here, 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 and here. The reason for that is that all the triangles involved get their altitude from our point x. So this line here, this turns out to be the altitude, and this will be the same for all 4 areas that we have to consider. This being said, we can cancel all the altitudes, and we are left with this expression, which is just an expression about oriented lengths. don't know if you recognize this, but this is really a great fact, because x does no longer occur in this expression. This only depends of the position of our 4 points, and we made the cross ratio completely independent of x. Once more, important fact, this only works as long as those 4 points are really in a collinear position. So after all, we have shown that the cross ratio is independent of x if we have 4 collinear points, and we can speak of the cross ratio of 4 points on a line. So it doesn't really matter if we take x or if we take another point x prime here, we will always get the same number as a cross ratio, and this number can be used to really do geometry just on a line. So I have to mention a few things about fractions and dividing by infinity here. So I always say the configurations I take should not be too degenerate, and in case of the cross ratio, it may easily happen that, for instance, 2 of those points, say for instance B and C, coincide. What happens if B and C coincide? Then this determinant here would become 0, and you would get some expression, something divided by 0. But remember, we are doing projective geometry, and projective geometry is the art of cultivating things that are infinite. And actually, in our setup, I will really allow that we divide a non-zero real number, like the 1 here, by 0, and simply extend the usual number field by one more value, infinity, and say, well, 1 divided by 0 is infinity. And conversely, 1 divided by infinity is a nice 0, and it should also be allowed to add 1 to infinity, and what you get is still infinite. You may even add infinity to infinity and still get something infinite. So these 4 rules I will use as a kind of additional way to deal with infinity. I have to make a little side remark here. You see this fraction here, and one way to think about that fraction would be something like a 2-dimensional vector. And you remember, fractions don't change their value if we scale the numerator and the denominator by the same value. So among those vectors, we identify scalar multiples. This is exactly what fractions do. And as a matter of fact, dealing with infinity in such a way really corresponds to considering this here as a 2-dimensional vector, thinking of it as a projective point, and this infinity here really corresponds to the situation that we have an infinity 0 in the last entry here, which corresponds to a point that is infinitely far away. So as a matter of fact, these cross ratios can be considered as points on a number line with some point that is maybe infinite far away. However, even in projective geometries, we said, okay, we don't want to admit vectors that are all 0. So here we really will include the case of 0 divided by 0 and infinity divided by infinity. They should be really degenerately undefined. And we will learn more about the projective number line in our next slot, where we really consider cross ratios as things that happen in, well, essentially a 1-dimensional place. So summing up, we can say if those 4 points are collinear, we can speak of the cross ratio of 4 points, we can define it as, well, the cross ratio seen from X for an arbitrary X which is not collinear with the rest. More about the number line, and we will treat that here as a low-dimensional projective space very soon in our next video section.